Hello, everybody. Today we're going to be introducing a very important topic, which is energy transformation. So it's basically, it's the main topic in this chapter, how to transform energy from one shape to another. First of all, we must introduce some basic information. There's a very important law that says that energy cannot be made or destroyed, but it can be transformed from one shape to another. And this is called the law of conservation of energy. So again, the law of conservation of energy states that energy cannot be made or destroyed, but can be transformed from one shape to another. So let's try an example. When you kick a ball, it will gain kinetic energy. We know that because any moving object contains kinetic energy. But you may think that the ball lost its energy when it stopped, because we know at a certain point the ball will stop, assuming that it was rolling on a horizontal floor. So you're saying that, okay, it had kinetic energy. Now it doesn't have any kinetic energy. So the law of conservation of energy is not very accurate because here energy was destroyed. Well, the term lost its energy isn't very accurate. What really happened to the ball is that the kinetic energy transformed into thermal energy due to the heat caused by the friction between the ball and the ground. So the law of conservation of energy still stands because the kinetic energy was transformed into heat or thermal energy. So energy transformation is all around us, and there are many examples for energy transformation. For example, when you turn on your stove, you are transforming chemical energy, which we introduced before as chemical potential energy, in the fuel into thermal energy. So that's a shape of energy transformation. Another example is when you turn on a fan, you're transforming electrical potential energy into kinetic energy, and the examples and shapes of energy transformations are infinite. Now we're going to introduce a very important term called mechanical energy. Well, we didn't talk about mechanical energy before. Is that a new form of energy? Actually, no. The forms of energy we talked about, we already finished them. What is mechanical energy then? Mechanical energy is simply the sum of all the kinetic energy and all forms of potential energy, because an object can have more than one type of energy in it at the same time. Again, an object can have more than one type of energy stored in it at the same time. And something very important about mechanical energy, it's that it is conserved. That means that the initial mechanical energy is equal to the final mechanical energy. Actually, what you said right now, it's not very clear. What do you mean by the initial mechanical energy and the final mechanical energy? Remember that we said that energy cannot be destroyed, but can transform from one shape to another. So the energy that transformed from the first shape, it's going to be equal to the energy that transformed to the other shape. So energy is transforming from one shape to another by the same amount. Say we had like 100 joules of kinetic energy when we kick the ball. Now when the ball stops, we will have 100 joules of thermal energy that was dissipated in the air. So that's what we mean by mechanical energy is conserved, and that initial mechanical energy is equal to the final mechanical energy. So it's very related to the law of conservation of energy. We can say that the mechanical energy is the kinetic energy plus the potential energy. Potential energy comes in many forms. Basically, we're going to be concentrating on gravitational potential energy and elastic energy. And as we said, that mechanical energy initial is equal to the mechanical energy finally. ME stands for mechanical energy, ME initial stands for initial mechanical energy, and ME final stands for final mechanical energy. Let's start with a very simple example. So let's say we have a ball that has a mass of 0.25 kilograms and was thrown upwards in the air. At the beginning, the ball is still on the ground. It has no speed. It's not above the ground yet. So we can say that it doesn't have any mechanical energy. The mechanical energy in it is zero because it doesn't have any kinetic energy and it does not have any potential energy. Say we gave this ball a push upwards, okay? The moment we gave the ball a push, what types of energy is going to be stored in the ball? In other words, what is the mechanical energy inside the ball? You are going to say the moment we gave the ball a push, we will have only kinetic energy inside the ball. Yes, assume we gave it a speed, say 8.9, and if we do a quick calculation, half mv squared, and we know that the mass of the ball, we already gave it, it was 0.25 kilograms. It will give me an answer of 10 joules. So we gave the ball a speed of 8.9 meters per second, and it gave us a kinetic energy of 10. Well, actually, the velocity here, it's not very important. So if you really don't understand what's happening here with the velocity, just forget about it. and concentrate on what's happening to the mechanical energy. So if I ask you what's the mechanical energy inside the ball, you're going to say, well, the mechanical energy is all the forms of the potential energy and kinetic energy. Since we only have kinetic energy here, it's equal to 10, and we still don't have any potential energy. Why don't we have any potential energy? Because the ball is still not raised above the ground. So when we're going to say the potential energy is equal to mgh, h in this case is still 0. So the mechanical energy, or sorry, the potential energy at this case is still 0. So the total mechanical energy is 10. Now let's look at the ball after 1 meter. It didn't stop yet, but we just imagine like we took a picture of the ball when it was 1 meter above the ground. And we did the calculations again. We found out that when the ball is 1 meter above the ground, and we calculated m multiplied by g multiplied by h, and we know that m was 0.25 kilograms. We mentioned that at the beginning of the question. We found that the potential energy is 2.5 now. From where did it get this energy? Because we said that energy cannot be made or destroyed, but can be transformed from one shape to another. So from where did the ball get the potential energy? Look at the kinetic energy. The ball is now losing its kinetic energy and it's gaining potential energy. So again, the law of conservation of energy still stands because the kinetic energy was transformed into potential energy. But why did the object lose some of its potential energy? Because we know that the farther the ball goes upwards, it will become slower. And since the kinetic energy depends on the velocity, the potential energy, or sorry, the kinetic energy will be less. So 2.5 joules of the kinetic energy were transformed into potential energy. Okay, let's study the mechanical energy. We know that the mechanical energy is all the forms of potential energy and kinetic energy. So if we add the potential energy and the kinetic energy, we get that the mechanical energy is 10. And we can see that they are equal in both cases because we said that the mechanical energy initial is equal to the mechanical energy final. Let's do this again at 2 meters. It's kind of becoming obvious right now. Half of the kinetic energy is being transformed into potential energy. So if we simply add them together, 5 plus 5 is equal to 10. So mechanical energy is still conserved. And at 3 meters, it's very obvious right now. And finally, when the ball reaches its highest point, we know that at a certain point, it will stop. So all the kinetic energy is now transformed into potential energy. As you can see, we started with kinetic energy equal to 10. Now it's 0. So if we add them together, the answer is 10. So we can see that the mechanical energy is always conserved. 10 equal to 10 equal to 10, etc. This will take us to a very important concept. As we can see that the mechanical energy was conserved the whole journey. It's very important to mention that we neglected air friction. So if we were going to say that the mechanical energy is conserved, we're going to say that there are no losses due to friction between the air and the object. So the mechanical energy final was equal to the mechanical energy initial. Now we saw that all the kinetic energy was transformed into potential energy. So we can say that the maximum potential energy is also equal to the maximum kinetic energy. The maximum potential energy was at the end and the maximum kinetic energy was at the beginning. If we put the equations of the maximum potential energy and the maximum kinetic energy, we can see that mgh will be equal to half mv squared. And we can cancel the m with the m here because it's for the same object. We can see that gh is equal to half v squared. This means something very important. This is proof that for any falling object, its velocity only depends on its height, not its mass. In other words, if we have an elephant and a feather and we toss them from a top of the building, they will reach the ground together. You're going to say impossible, but I'm going to say yes, it's possible, but we must neglect air friction. So if we can get a huge chamber that is vacuum with no air in it, and we threw a feather and a very huge object together, they will reach the ground at the same time. So this is one of the main examples on energy transformation. Stay tuned in the next videos where we will be talking about other shapes of energy transformation that are mentioned frequently in the exams. So see you then.